Hi, Assalamualaikum warahmatullahi wabarakatuh. I'm Huzaifar Darwis and I'm from RS2034B. So the first journal that I chose for this video assignment is core branch ferric hydroxide oxide carbon nanotubes composites for high performance supercapacitors. So let us take a look at the problem statement. The transition metal oxide has poor electronic conductivity, limited contacting area, and serious structural deformation without carbon materials. And in this journal, the objectives is the first one is to enhance the electrochemical activity and mechanical integrity of TMOs, which is the transition metal oxides. And the second objective is to improve mesoporous properties of transition metal oxides to overcome its structural limitations. So this is the result and analysis. As we can see over here, this is the first figure. And in the first figure, three ferric hydroxide oxide CNTs composites with 75%, 70%, and 65% ferric hydroxide oxide content were designed as ferric hydroxide oxide CNTs 1, 2, and 3 from high loading to low loading. In figure 1a, it can be seen that the ferric hydroxide oxide nanoparticles show a spindle-like morphology with an average size of 150 nanometer and a diameter of about 20 nanometer. In figure 1bc, it can be observed that the ferric hydroxide oxide is uniformly arranged in a thorn-like shape along the CNTs, the carbon nanotubes, in ferric hydroxide oxide CNTs 1 and 2. With a larger amount of CNTs, the ferric hydroxide oxide is not evenly deposited on the surface of CNTs in ferric hydroxide oxide CNTs 3. And some carbon nanotubes are bare as shown in figure 1D. The TEM images of the product are shown in figure 1EF, further confirming the proposed core branch structure. It clearly shows that the obtained ferric hydroxide oxide crystallizes with spindle morphology aligned uniformly on the CNT surface, and the ferric hydroxide oxide shows an average diameter of 10 nanometer and an average length of 60 nanometer. High resolution TEM micrograph is shown in figure 1G. The spacing of the observed lattice planes are approximately 0.741, 0.254, and 0.247 nanometer, which are consistent with the spacings for the 110, 211, and 330 planes of the ferric hydroxide oxide 1314. The selection area electron diffraction SAED pattern in figure 1H presents a broad and diffuse halo ring, which can be indexed to diffraction of 321, 330, 501, 611, and 651 planes of ferric hydroxide oxide and 002 plane of CNTs. Okay, let us take a look at the second figure, figure number 2. Okay, so this is the second figure. Figure 2a shows the X-ray diffraction XRD patterns of the as prepared ferric hydroxide oxide and ferric hydroxide oxide CNTs. All diffraction peaks can be perfectly indexed to the beta ferric hydroxide oxide structure, and the diffraction peaks of CNTs is covered by the ferric hydroxide oxide. Obviously, the diffraction peak at 26.2 degree becomes wider with the increasing amount of CNTs in the composite. As shown in figure 2b over here, the thermogravimetric analysis TGA is employed to measure the amount of ferric hydroxide oxide growing on the CNT surface from room temperature to 1000 Celsius under an air atmosphere. The final remaining mass refraction of ferric hydroxide oxide CNTs 1, 2, and 3 are 62.8%, 56.6%, 52.5% respectively. Based on the weight loss of CNTs and pristine ferric hydroxide oxide, the contents of ferric hydroxide oxide in the ferric hydroxide oxide CNTs composite are calculated to be about 75.5, 70.75, 65.62% respectively. X-ray photoelectron spectroscopy (XPS) measurement is carried out on the ferric hydroxide oxide CNTs2 to study the surface composition and oxidation states of the elements. So in figure S1, the full spectrum shows the existence of carbon, oxygen, and ferrum. Figure 2c shows the C1 spectrum, which can be divided into four constituent peaks. The strong peak at 285 electron volt corresponds to graphitic carbon in CNTs. The XPS spectrum of the O1 region can be divided into three peaks, including ferrum-oxygen-ferrum bond, which is 529.8 electron volt, and ferrum-oxygen-hydrogen bond, which is 531.8 electron volt in figure 2D. The ferrum 2p region in figure 2e shows two major peaks located at 711.6 electron volt and 725.2 electron volt, with two satellites at 719.5 and 733.2 electron volt. To further understand the surface area and pore structure of ferric hydroxide oxide CNTs, we compare the difference of ferric hydroxide oxide and ferric hydroxide oxide CNTs2 by the nitrogen gas absorption-desorption curve and the pore size distribution in figure S2 and figure 2F. The BET surface area of ferric hydroxide oxide and ferric hydroxide oxide CNTs2 are 90.6 at 4 meters square per gram and 96.225 meters square per gram. And importantly, the PSD shows the pore size of ferric hydroxide oxide CNTs2 continuously distributed in 2 to 20 nanometer, which can be more conducive to the occurrence of the reactions in the complex structure. And apparently, the areas of ferric hydroxide oxide CNTs are much larger than that of ferric hydroxide oxide in CV curves. As shown in figure S3, a change in the hysteresis of redox peaks can be observed with a steady increase in scan rate. According to the discharge curve in figure S4, all of the discharge curves display well-defined voltage plateaus, and the ferric hydroxide oxide CNTs2 show the longest discharge profile with a high specific capacitance of 1550 F per gram and 1 A per gram, which is higher than the other sample at the same current density. Okay, let us take a look at the third figure in this journal that I have found. Okay, so this is the third figure, A, B, C, D, E, F, G. G is at the bottom. As the comparison of discharge curves of ferric hydroxide oxide CNTs 1, 2, and 3 in figure 3b, the specific capacitance are 155 F per gram, 1380 F per gram, 1540 F per gram, and 450 F per gram at 1 A per gram respectively. To evaluate the cyclic stability, galvanostatic charge uh, or discharge tests are performed at 5 A per gram for 3000 cycles. The ferric hydroxide oxide CNT2 composite maintains around 83.4% of the first cycle after 3000 cycles. This indicates a good electrochemical stability. Figure 3DE shows the calculated specific capacitance based on the discharge curves at different current densities. The ferric hydroxide oxide CNTs2 electrode exhibits specific capacities at 1550, 1550, 1500, 1450, and 1380 F per gram at the different current densities of 1, 2, 5, 10, and 20 A per gram, respectively. Electrochemical impedance spectroscopy (EIS) is performed to understand the resistance of ferric hydroxide oxide and ferric hydroxide oxide CNTs electrodes, and the Nyquist plot of different electrodes was displayed in figure 3F over here. In the high frequency range, the intersection of ferric hydroxide oxide CNTs is smaller than that of ferric hydroxide oxide, suggesting that the ferric hydroxide oxide CNTs show lower equivalent series resistance (RS). The resistance of ferric hydroxide oxide CNTs is smaller than that of ferric hydroxide oxide. That indicates ferric hydroxide oxide CNTs electrode shows higher electrical conductivity. In summary, as schematically illustrated in figure 3G, during the charging-discharging process, the conversion of ferrum 2 plus and ferrum 3 plus can be fully carried out on the uniformly distributed ferric hydroxide oxide, and electrons can rapidly transfer along the carbon skeleton. Therefore, the co-branch structure of ferric hydroxide oxide CNTs greatly promoted the improvement of its electrochemical performance. So, in conclusion, the core branch ferric hydroxide oxide CNTs composites were synthesized with several advantages as electrodes for supercapacitors. Number one, benefiting from the confinement effect and special electronic influence of CNTs, the in situ ground of ferric hydroxide oxide along the CNTs disperse more evenly, and a satisfactory core branch structure can be obtained. Number two, due to the support structure of CNTs, ferric hydroxide oxide CNTs, composite has the interconnected skeleton and sufficient pores, which alleviates volume changes, improve the mechanical properties, and form a conductive network. Number three, the CNT's carbon nanotube substrate contributes to enhancing the electrical conductivity, leading to a fast transmission of electrons or ions and an excellent electrochemical performance. Okay, so this is the conclusion of the journal that I have read for this video assignment. Thank you so much for your time. Thank you, madam.